Earlier, we've seen how we could create a motion graph starting from one big animation. And today, as an introduction to reinforcement learning, we will see how we could use that motion graph to build a runtime animation controller. Hi, I'm Jerome, and today's paper will be Precomputing Avatar Behavior from Human Motion Data, a paper from 2004. So the idea of that paper is to start from a motion graph. So what I've done is that I've saved a bunch of information from the notebook with the motion graph. So I don't have to recompute the motion graph from scratch. I will already have all the transitions and all that kind of stuff saved for me. So what I've done is, of course, loading all the libraries, and then I will load my character. And I've also added all the foot contact, so I can do a quick IK pass to stabilize my foot at runtime. I have sphere for debug, and here is the informations I have from the motion graph data. So I have the animation that I've used to do that locomotion. I have the window size that was used. I have the frame validity, so I know inside of that big animations which frames are meant to be used and which are invalid. I had a bunch of range that I didn't want to use. And I get the local minima, so basically all the time, all the places where I could have transitions. So that's all information coming from the motion graph. What I will do is quickly compute the foot contact again, so I know when I have a contact on the ground. And as a reminder, here is the animation that was used to build the motion graph. So this is the entire animation here. So a bunch of locomotions walking along, and then see, that's the range that I don't want to use, the teleportations. And then I get higher turns, smaller turns, and all that kind of stuff. So that's what was used when we were doing the motion graph. Now, I will recreate the motion graph here. I only have all the transitions possible. But what I would do is that I will do it the same way as the paper has done it in this case. So instead of using the motion graph with every node being a bunch of frames and every edge being the jump where you could go, what we will do is that we will turn this graph into a state and action graph, which is tons of terms that you will hear a lot when we start to talk about reinforcement learning and all of those. So now it's a bunch of states. So instead of having all my frames of animation that jump, I only have the state, and the state represents one frame where I can take a decision. So it doesn't represent an animation anymore. It represents a pose. And the action itself is the animation you could do to reach the next state. So each state is one pose, and each actions are actually the animations that lead to the next state. So I will build the graph in this way. So I will have a state, and each state will have a bunch of actions, and the actions will be knowing the starting frame of animations and the end frame of animations. So that really the action itself that has the animations. And the way you compute this kind of stuff, basically, you start by creating an action of one frame between every state, as in this case, all the bees. So you create all the actions. Then you add, what I've done is I'm adding all the transitions that were coming from the computed motion graph that says you could jump from here to here and that kind of stuff. So that's all the action that represents the jumps. And then you will, you basically pick one of any states, and then you check its first action, and then you check the state, and if that state has only one action, you basically collapse the edge. So you make the edge longer and longer and longer, and then basically all the states that don't have any edges anymore are discarded. So that's how I've done it here. I get all my edges, and then I start to collapse them if they don't have anything that need to lead to. And when you've done all of that, basically you end up with 540 different states. So that's the number of states I have. And each of those states have at least 2 actions they can pick from. What I will do then, because I have all those states, and the states themselves are the actual animations, I will start to pre-compute a bunch of stuff on those states just to make my life easier when I will keep going through the paper and I need to play back a bunch of stuff. So what I will do is that now every actions, I know exactly where they start from and up to where they go. So I will store the trajectory of the root motion directly in the state. Remember, my animations is all over the place in world space, and I only want to be able to move everything into local space. So everything I will do is that every start of the actions, I take the first position as being neutral and bring it back to 0, 0, and I take the trajectory as a local trajectory based on the first frame. And thanks to that one, I can have a local trajectory that basically is just the amount of displacement I have along every frame. So when I would want to play back the animation, the only thing I have to care about now is always adding the amount of trajectory, local trajectory at every frame. I don't need anymore to compute all the transform, bringing back the character, realigning them, all that kind of stuff, because basically all my motion is local to the previous frame that was played anyway. So that's what I'm doing here. I go through every states, I go through every actions, and then I pre-compute the local trajectory. So all of that now is local to the frame of the state itself. And then I compute the local trajectory, that's just the offsets between frame to frame, and I store that inside of the action. So now my action has the trajectory it expects. And what I will do, so far, every time I was doing a paper, I was pre-computing an animations and playing back that animation. Now what I want to be able to do is to be runtime. So I will actually create an animation player, which just means that I stored information of which frame I'm playing, and what is the positions I'm in space. And then I will have the footlock mechanism. Basically, that one is just really a simple IK that just check if the foot, or it's even only checking if the toe is on the ground. And if it is, I don't allow it to move from frame to frame. And then if it's not, I just release that IK with a blend just to get a soft release every time I connect. And then the animation player itself basically knows which action is playing. It knows the frame of inside of that actions, where am I inside of along this action. I get the position and quaternion, so really the pose of the character that it computes. I know which frame was played last. If I'm doing a transition, so am I blending between 2 animations and that kind of stuff. And so what happens is that you tick it every frame saying, I need you to compute the next frame. And if it has an action, it goes and plays the next frame of that action. And when you reach the end of the action, it just put the actions to none and says, I have nothing left to play. And what happened is that you could set an action and basically you add the new action to the next step and so on and so on. So that's what the player would do. And if we go and see what happens now, I get the animation player, so I will start from my player. And the only thing I will do is that I would tell him, you tick the player. The only thing that if you don't have any action to do, you basically check in which state you should be. You pick randomly any action inside of that state, you set that action and you play and you tick the player. So now you could see it will randomly play any animation from there. And what I can do is I can force him to keep playing, and the player will basically keep playing. So now the timeline doesn't represent anything in my case, it's just runtime playing animations. And then that's the character randomly picking an action every time it finishes. Every time it reaches a state, it randomly pick an action. It will go not anywhere. We did the same with the motion graph. We walked randomly the motion graph. It's exactly the same concept here. Nothing really fancy is happening. So what we have is a motion graph that basically is a bunch of states. And in each of those states, you could take a number of actions leading to the next state. Now, what we want to do is to build a control policy that will allow us to pick the best action to do depending on a certain target, a certain goal. So if I want to have the character walking along and being able to say, I want you to walk and go there, basically, so that's the goal, is to say, I want him to walk and reach that point. I will do the same stuff that they've done in this paper, which says that they wanted to make the boxer, in this case, walk along in the ring to reach the character they had to box with. So what we will do is that we will discretize the world around the character and giving him a bunch of different targets that are a bunch of goals you could reach. So basically you will say there is a point 20 centimeters in front of you, find the best actions that will make sure that we walk next to that point. I will have another point that will be 1 meter away, give me the best actions that will actually make me reach that point, and so on and so on. And it's set up in circle around the character, and that gives you a bunch of points that you could start to find the best animations that will allow you to reach any of those points. So at runtime, I will be able to say, I need you to go 40 centimeters on your left, and then it will give me the best animation that allow me to do this kind of stuff. To do this, basically what you do is that you create a reward function saying, for every of the possible action I have, this is the one that gives me the best result compared to the target you were asking me to do. So what happened is that we have a reward function, and that reward function is basically depending on the states you're in and the action you pick. So for every state you're in and for every action you can pick, this is the score, this is the reward you will get. And how they compute this one, so basically what you have is the reward functions. It depends on the state, so the current state of the character. It depends on the target state, so which point am I trying to reach? And then it depends on the action that was taken by the avatar. And what you try to do is you would basically take the position of the character along the trajectory. That's why I saved the trajectory in local space to that action. I will have the point along that trajectory and the point from the target. So the point 10 centimeters in front, the one 1 meters in front, and so on and so on. And I compute the distance of those, and then put them through an exponential. And then finally, I have the discount factor. So it's a value that I will use to say the longer the animation is, the worse the reward gets. So if you manage to reach the point in 10 frames, it will be much better than if you reach that target in 100 frames. So because you get the exponential here, it will go down fairly quickly depending on the length of the animations. And then the reward will actually be the maximum value you could find along that path. I will say for that trajectory, at some point, it will be really close to my target. So that will be the max T. But again, it finds the best score between long or short term and the closest positions. So that will be the reward function I will be computing. So what I would do is compute a bunch of stuff. The first thing that I'm interested in is knowing what is the maximum number of action any states can take. And actually I have at least one state that has 7 actions. And the second one is the longest action I have, and the longest action is 23 frames, so nearly 1 second of animations, the longest actions. So as they have in the paper, so they said I have a bunch of points around me. So this is what I would do. I would create the target's positions. So all the points around me. So I'm starting from 0, 0s, and then I go in circle with different ranges, and I get more points the further I am. And so that gives me 64 different targets. So 64 different goals I can reach. And then I will compute the immediate reward. So I will compute the reward with the formula I had here. So basically what you have, you get the rewards for each state, for each target, for all the maximum action count. So all of my states have a different number of actions. In this case, to make my life easier, I just take the maximum. So I create a big table, even if most of those points will be -1. So a really bad reward, basically because you're trying to take an action that doesn't exist. So I get the -1 by default, says that will be the action you will never take. And to win sometimes later, at the same time, I compute my next states. So what I do is that I know the trajectory of each of my action. So I know that if I was in a specific state, trying to reach a specific point, and I played these specific actions, the next one anyway will always lead me to the same point, and that will be that next state in the state space. So what I've called the state space, normally when you do reinforcement learning, you get a table of state and action, and basically state count and target position count all becomes one big state space. So if you check what I've done here, is that I've computed everything using the states and the targets separately, and then the action. But then when I'm reaching here, what I've do is that I've reshaped the immediate reward and next states as being just a mix of all the different states. States becoming, in this case, the character position and the target I was trying to reach. That becomes only one single state. So that's why when I compute the next states, I do it this way. So I get only one value. The next state is one value, is really one state, right? So I have the immediate reward and the next states, and so I can actually load my gamepad. Okay, so I can use my pad now to control my character. And what I will do is that I will play the animation using that reward. So what happened is that if I don't have any action, I check the states I'm in, and then from there I compute the I find the closest position, the closest target I could have. So everything was computed in local space. So every time I'm in a state and I'm asking to reach a certain point in world space, I need to convert that position relative to me and then find the closest target I could get. So that's what I'm doing here. I convert the position to be relative to me, and then I take all the target's positions, and I try to find which one I'm the closest one. So I take the distance and I find the minimum, the argument, so the minimum argument inside of that list that gives me the target state I'm trying to reach. And then I can just pick the reward. So I go with my reward and I say I'm in this state with this target state. I get a bunch of actions I can choose from, give me the one that gave me the best reward. and then that will be my action. And I get my selected positions and all that kind of stuff, just to let you see what I'm playing with. So what I have is this. I get a bunch of stuff on the ground. So I get my ball, which is the target I'm trying to reach. All those little transforms are all the different targets that are possible. And the big one is the one that right now I'm trying to match, because that's the closest one to the sphere. And so if I play my animation, you could see what you have here. And so the grid only moves every time there is a state and every time there is an action that is taken. So you could see it always tries to reach the closest one. And the black line is the trajectory projected on the ground that represents the length of the action it takes and what it does. Now, what I could see is that with the immediate reward, it kind of stay close to that red ball, but really, even if I move it, it tends to do whatever it wants. Every action it picked gives him the best solution to get the closest to the target he wanted to be, but he might get stuck into a weird state instead of the motion graph. That means that even his best action would actually make him walk in the wrong direction. So that's, you could see that's what happened. He managed to get close. He reached a bunch of states that had big locomotions, so he was able to walk, but then see, he's stuck on something that loops and is not even able to come here. So right now my policy to only use the reward you get from get me the best action is not really accurate, doesn't give me any good results. And that's where we will start to talk about reinforcement learning itself. Now, what you want to realize is that the state and action we have now is actually what we call a Markov Decision Process, or MDP in short. And an MDP basically means that any action you can take only depends on the state you're in. You don't care about the past and how you reach that state. The only thing that matters is what is the goal you want to reach, and what are the actions that are available to you depending on the states you're in. So it only looks forward. And so the Markov decision process basically has a state and has a set of actions, and you get the reward functions by taking one actions depending on one state. You get a discount factor, which basically says how important the future is. And then you get the transition functions that tell you, well, if I was in one state and I took one action, what is the next state I'm in, basically. And the goal of the MDP is to find a policy that basically maximizes the cumulative reward along the future. So the real function is this one. You have your gamma again here that reduce. So at T0 means the first transition you take is the most important one. And then every time you advance one step further, this one will decrease. And you will have the reward for the next state that pick the next action, and then the reward for the next state that pick the next action, and so on and so on. And what we're trying to find is to maximize this sum of infinite possibilities you have and find the best trajectory through all the states and actions you could take that give you the maximum cumulative reward. That is impossible to compute because it's an infinite sum. So we need to find a way to compute that kind of stuff. And what we do usually is that we use the value function. What is the value functions? It basically stores the best reward you could have if you are in one state. So it gives you what you want to do is it basically tells you the maximum score you could have to pick any of the action you have because you are inside of one state. So that's your immediate reward, plus the discounting factor of the next state that already knows what is the best action reward you can have. So it is an iterative process. Basically, you have the immediate reward plus the future reward, but the future reward is actually computed with the same value functions as the one that you have here at this point. And thanks to this formulation, we have the Bellman update rules that basically says that you could just compute this as long as your gamma is less than 1. You could iteratively compute this stuff and update the value every time you take one of the actions, you check the future, you update your values, you take another action, take the futures, and so on. And you can update your value functions and you will converge to a solution. So it starts from picking randomly any state action pair, compute the reward, estimate the value of the future reward, and then update your value functions. What I've done is that instead of have the value function that's only have states and best actions, what I will do is that I will have value functions that have the states and each of the action, and I will compute all the actions separately. It's just to make the code easier to read here. So basically what you do is this: you randomly pick any states, any action, then you compute the length, you take the reward, and I've pre-computed the reward, so at least I don't have to recompute that same reward as every time. So I've pre-computed the reward, I get it. I also pre-computed what was the next state, so I already have the next state. And I can find the maximum values. So I will go from my value function I'm computing, get the next states, find what is the best value I could ever dream of in that case, and that's my next max. And I can update my value function with a reward plus the next max plus the future reward discount. And what they used as a discount was that's YT, yeah, that's what that here. So they've used the gamma again, and it's multiplied directly by it's a power of the length of the animation again. So if your action is really long, your future reward anyway is less. So instead of just taking the length of the number of actions you took, it's actually the length of the animation itself that matters to reach. Then you could see that I'm slowly converging because the amount of values I have in total in my value functions doesn't change, even if I'm actually computing 30,000 different action state pairs. It did converge, and well, quite close to a conversion after 270 epoch. So I've recomputed that value functions every time. And now that I have the value function, well, instead of picking the immediate reward as I was doing before, I can just use my value function, and then we could see if the future reward makes the system a bit smarter to go and pick the next animations. So let's see. So I'm walking around, could see that it goes back to the blue sphere a bit faster. And if I give him a target now, I will actually try to reach it a bit further, or at least nearly in straight line when I give him a target. And I can start to annoy him a lot, just changing direction all the time. And as a reminder, if I go back to the immediate mode, this is what happened. It tends to play and live its own life, doesn't care about my targets. And if I ask him to go back with the value functions, here it is going back to the right direction. And so we've trained our first animation controller. Basically, it is now it has a value functions that allow him to pick the next best action using the future reward. But something you might have noticed is that in this case, I've actually been able to switch from the immediate mode to the value functions. And that's basically because when you train a policy like this, the policy just tells you which action you have to take depending on the state you're in. And so you could use different sets of policies depending on the stuff you want to do inside of the same motion graph. So you will have always the same states, always the same actions. The only thing you want to change is how you pick the best action. So something I don't really like in this case is that it's not really able to go on the target and stays on the target. What I want to do is to basically says, if you're close to the target, you go in idle mode and you stop walking. Unfortunately for me, I don't have in my motion graph any idle animation, because when we did the motion graph earlier, it was to do locomotion. So it basically walks all the time. But there is something at the end of my animation here that basically says from frame 950 to frame 1200, it would stay around this spot and just do small steps. So what I would do is that instead of saying go in idle, because I don't have any, I would say go play those frames of animation when you're close to the target, just stay close and play that. So I could train another policy. So what I would do is that instead of having my value functions, the one that makes me walk, I will do a second value function that I will call value function static. Basically says stay on the spot as best as you can. And this one only depends on the states. Now there is no target anymore. It's just you are inside of an animation, and if I tell you to stop, that's the action I wanted you to do. There is no targets anyway. So my value functions is way smaller in this case. It only has state count and max action count. My reward itself is always 0, except if you were playing animations that started inside of that range and ended inside of that range. So really, I want you to play actions inside of the end of the range, and that's it. And then I propagate the same way. I take the next states, find the next maximum score I can have. I have the same future reward discount depending on the length of the animations, all the same. And then I can compute this reward. And you can see that it converts really quickly because basically everything is 0 and the end of the animation is 1, and you just have to propagate those weights. And now what I do is that I don't control in which state I want to be manually. The only thing that happens is that if I'm close to the goal, if my position is close to the goal, I just, so at less than 50 centimeters, I will start to use that policy that says stay next to it. And if I'm further away, I use the walking policy to reach the goal. And so if I'm here and I ask him to play, this is what I would get. So the green one means stay in spot, and you can see it plays basically that end of animations. It just stays and plays inside of those animations. And the way the value functions was computed, it even give you best scores if it keeps playing along the animations, because I will have a score of 1 for being inside an animation, but I will get a big reward because the next one was also in the same range, and I will get a big reward because the next one was also in the same range. So it will tend to play forward. You could see that even here, that represents the frame is playing, that represents the transition is taking. So you could see it keeps playing all the range and then change every time to go back to the beginning. So that's that loop that gives him the best reward. And if I move away, it will go and it will start to walk into that direction. And as long as if it gets close, it goes back to the other one. And I can come back here and it will walk again, coming back to the to the targets and stop to the targets. So that's the advantage of having this kind of stuff. You could change policies and depending on how you could do. See, it walked too far, it gets closed again, and so on and so on. Because there is nothing that forces him to not drift when he walks. So it will actually, from time to time, drift away from the target. And that's it. We've trained 2 different policies on one motion graph. And you could think of any type of policies doing different stuff. What they've done in the paper, it was a boxing one. So you have all the different points where we can punch, and you could of course ask him to punch a specific point, and he will move along, punch it. Unfortunately, I didn't have enough punching animations inside of my libraries, so I've stayed with the locomotion one. But there's a lot of stuff you could learn, and starting from here, basically what you will have is 2 different directions that the paper will start to go. They will get the branch that will try to get a better motion graph with a lot more connections inside of a motion graph, because the more connections you have is the more states you have, is the more is how quickly you could react, because it's all the time you could actually take a decision. You can only take decision at each action. So you will try to have a higher number of connections inside of your motion graph. That's one of the direction. Then you will get the other direction that will say, what we want to do is to find another type of structures that allow us to have more and more actions, having actions smaller and smaller and smaller. And so you could take decisions more often. And so the maximum range you could have is at some point you will have that every frame would be a state and an action, and you will be able to take an action at every frame. So that will be for in a few paper. And basically what will happen when you will have all this, you will start to reach what the motion matching is, which was the next step. Says the first step was to say I remove the motion graph and I have value functions that use reinforcement learning on. And then the motion matching would basically say, well, I will remove the reinforcement learning, but I will still have basically a value functions. We'll just see that it's not learned through the same process. It's extracted from the animations, but the concepts are the same. So that's why I love to go through those steps before reaching the motion matching. I hope you liked it, and see you in our next paper about animations and reinforcement learning that will be slightly different.